The Boeing 707 was not just revolutionary because of its speed, but because of what was hidden inside its structure. Every internal system was designed to handle pressures, temperatures, and forces that commercial aviation had never faced before. At the heart of the Boeing 707 were its four turbojet engines, originally the Pratt & Whitney JT3C, and later the more efficient JT3D turbofan engines. Inside each engine, air entered through the intake and was compressed by multiple axial-compressor stages. This compressed air was mixed with fuel in the combustion chamber and ignited, creating high-energy exhaust gases that passed through turbine blades. These turbines powered the compressor and produced thrust. Compared to propeller aircraft, these engines delivered continuous, smooth power at high altitude, allowing the 707 to cruise above weather systems and turbulence. Fuel delivery inside the Boeing 707 was a complex and carefully balanced system. Fuel was stored in multiple tanks located within the wings and center section of the aircraft. Internally, fuel pumps ensured a constant flow to each engine, while cross-feed valves allowed fuel to be shared between engines if one system failed. This internal design increased safety and allowed pilots to maintain balance by controlling fuel distribution during flight. One of the most important internal innovations of the Boeing 707 was its pressurized cabin system. At cruising altitude, outside air pressure is too low for human survival. To solve this, the aircraft used engine bleed air, which was cooled, filtered, and pumped into the cabin. Inside the fuselage, the pressure was maintained at levels equivalent to lower altitudes, allowing passengers and crew to breathe normally. The circular fuselage cross-section was specifically designed to evenly distribute pressure stress, preventing the metal fatigue problems that had plagued earlier jet aircraft. The flight control system inside the Boeing 707 combined mechanical linkages with hydraulic power. When pilots moved the control yoke or pedals, cables and rods transmitted those movements to hydraulic actuators. These actuators amplified pilot input, allowing control surfaces such as ailerons, elevators, and rudder to move smoothly even at high speeds. Without hydraulic assistance, controlling a jet of this size would have been physically impossible. Hydraulic systems also powered the landing gear, brakes, flaps, and spoilers. Internally, the aircraft had multiple hydraulic circuits to ensure redundancy. If one system failed, another could take over. This redundancy became a standard safety principle in modern aviation, and the Boeing 707 helped establish it. Inside the wings, the structural design was equally advanced. The wings used strong internal spars and ribs to handle lift forces and engine weight. Fuel tanks were integrated directly into the wing structure, reducing weight and improving efficiency. The swept wing design helped delay shockwave formation at high speeds, allowing the aircraft to approach transonic flight without losing control. The electrical system of the Boeing 707 was powered primarily by generators driven by the engines. These generators supplied electricity to the cockpit instruments, navigation systems, cabin lighting, and communication equipment. Internally, electrical buses distributed power across the aircraft, while backup systems ensured essential instruments remained active in case of generator failure. Navigation and avionics inside the cockpit represented a massive leap forward for their time. The Boeing 707 was equipped with gyroscopic instruments, radio navigation receivers, autopilot systems, and weather radar. These systems allowed precise long-distance navigation across oceans, something that had been extremely difficult with earlier aircraft. The autopilot could maintain altitude, heading, and speed, reducing pilot workload during long flights. Environmental control inside the cabin went beyond pressurization. Air conditioning systems regulated temperature, humidity, and airflow. Insulation within the fuselage reduced engine noise and vibration, improving passenger comfort. This internal comfort played a major role in making jet travel acceptable to the public. Even the braking system inside the Boeing 707 reflected advanced engineering. The aircraft used hydraulic-powered brakes with anti-skid protection, allowing safe landings at high speeds. Internally, sensors monitored wheel rotation and adjusted braking pressure to prevent tire blowouts and runway skids. All of these internal systems worked together as a single integrated machine. The Boeing 707 proved that a large jet aircraft could be reliable, safe, and efficient for commercial use. Its internal architecture became the blueprint for nearly every jetliner that followed. Modern aircraft may use digital systems and lighter materials, but their core design philosophy can be traced directly back to the internal engineering of the Boeing 707.